So if a city needs water, you generally you build a dam.
Right.
And if it needs electricity, you build a massive power plant. Like, we have this deeply ingrained assumption that solving a really big infrastructure problem means just, pouring thousands of tons of concrete.
Yeah, absolutely.
So naturally, when we look at the global transition to electric vehicles, the default assumption is that we just need to dig up the sidewalks and build millions of permanent fixed charging stations everywhere.
Well, it's a very 20th century way of thinking.
Yeah.
We are so used to the gas station model, you know, a fixed destination where you physically drive the vehicle to the fuel.
Right. But the infrastructure of the future, it isn't going to look like a gas station.
Not all.
It is rapidly becoming something completely invisible, highly mobile, and making these really complex energy decisions in milliseconds.
Right.
So welcome to today's deep dive, everyone. Today is Monday, August 24th, 2026. And if you're listening to this, you probably noticed those shiny new EVs everywhere.
They are everywhere.
But today, we're taking you past the sheet metal. We're going to uncover the invisible infrastructure that is actually keeping this whole ecosystem from collapsing. And we have a great stack of sources today.
Oh, yeah, it's a deep stack.
I've got a University of Tennessee research paper on EV charging, an APM Terminals press release, some AAA member updates, Autotech Insight industry dispatches, and a really interesting set of technical blogs from Synop.
The Synop ones are fascinating, but what's fascinating here is how the scale of the challenge is actually what forces this innovation. Because we are moving away from centralized power distribution into this really chaotic, decentralized network.
Right.
And the physical realities of the power grid are basically forcing engineers to get incredibly creative.
Okay, let's unpack that scale for a second, because I was looking at that University of Tennessee research paper.
Yeah, the modeling.
Exactly, their modeling. They point out this massive issue. We expect 10 million EVs sold globally by 2025.
Right.
And by 2040, they expect 57% of all passenger vehicle sales to be electric.
Which is just a massive volume of cars.
Right. And the immediate realization when you look at those curves is that we cannot pour enough concrete to build fixed charging stations for all those cars.
No, you really can't.
The local grids simply cannot support putting a fast charger on every single corner. So the solution they propose in the paper is something called a mobile charging station, or MCS.
Yeah.
It's essentially like a giant power bank for your car, right?
That is exactly what it is. And it's a beautiful inversion of the traditional model, because instead of the vehicle traveling to the power source actually travels to the vehicle.
Wow. Okay. So the mechanics of it are fascinating. The researchers break these down into a few distinct categories from what I saw.
Right. There are a few different types.
So you have the TMCS, which is the truck mobile charging station.
Yes.
And sometimes they just act as like a massive extension cord for an overloaded fixed station. But the really capable ones carry a BSS, a battery energy storage system, mounted right on the truck chassis. And then there are portable mobile charging stations, or PMCS, which are basically standalone heavy-duty batteries that are just towed by a vehicle and dropped off wherever they're needed.
And the engineering behind those battery storage systems is really complex.
I bet.
But the real genius, I think, is in the grid economics.
How so?
Well, think about the massive financial risk of building a permanent charging station today. You have to secure real estate, right?
Yeah.
You trench high voltage copper lines, you upgrade the local transformers, and then you pour concrete.
Right.
All while just basically crossing your fingers that EV drivers will actually use that specific intersection.
Right. It's a multi-million-dollar gamble, just hoping people show up.
Exactly. But a mobile charger, it acts like a pop-up shop for electricity.
Oh, I see.
So an investor can deploy a towed battery station to a new neighborhood for a month. And if the utilization rate is high, they know it's safe to build permanent infrastructure there.
Right. It's like a pilot test.
Yeah, and if no one uses it, they just hitch it up and move it to a stadium for a weekend football game or something.
Oh, wow. That's brilliant. And it also completely changes how we draw power from the grid, right?
Yeah.
Because instead of demanding a massive spike in electricity right at 5 p.m. when everyone gets off work.
Yes, the peak hours.
Right. These mobile stations, they can be plugged in at an industrial park at like 2 a.m.
Exactly.
So they sip cheap, abundant off-peak electricity all night. They store it in their onboard batteries, and then they just drive into the city center during the day to dispense it.
It completely flattens the power grid's demand profile.
Wow.
The grid doesn't experience the shock of a dozen cars suddenly requesting fast charging all at once, because that mobile unit has already buffered all that energy.
And we're actually seeing this move from academic models into everyday utility. I mean, AAA is already doing this.
Right, the Motor Club.
Yeah, they've actually integrated this into their standard service.
Yeah.
So if you're a member in cities like Orlando or San Francisco or Denver, and you run out of juice on the highway, they don't tow your car to a station anymore.
Oh, really?
Yeah, they dispatch a truck equipped with a mobile EV charger to give you a 15-minute top-up at no extra cost.
Wow.
Just enough range to get you home or to a fixed plug. It's a completely seamless transition for the consumer.
And the consumer application is highly visible. And early innovators like Nation E back in 2010.
Oh, yeah, 2010.
And then VW Neo Tesla, they have all deployed various forms of mobile chargers. But consumer convenience is really just the tip of the spear here.
Right.
The true stress test for the grid isn't a family SUV needing a top-up on the side of a highway.
No, it's the global supply chain.
Absolutely.
Because if I'm a massive commercial fleet operator, I can't just call AAA if my semi-trucks run out of juice.
No, they are not bringing a battery pack for a semi.
Right, so how are the big players handling this transition? Because if passenger cars cause range anxiety, heavy-duty commercial fleets have to cause full-blown grid anxiety.
They absolutely do. If we connect this to the bigger picture, a single heavy-duty electric truck requires a staggering amount of kinetic energy to move, tens of thousands of pounds.
Yeah.
So when you try to electrify hundreds of them in one place, the energy requirements look less like a gas station and more like a small aluminum smelting plant.
Wow. I mean, look at the news from APM Terminals, Elizabeth, at the Port of New York and New Jersey.
Right, the port modernization.
Yeah, this single terminal handles 28% of the port's entire container throughput.
Yep.
We were talking about 800,000 truck visits a year.
That is massive.
And on August 18th, APM announced this huge investment. They're bringing in 96 electric terminal tractors from Orange EV.
Oh, wow.
Yeah, these are the heavy haulers dragging those giant shipping containers around the yard. And on top of that, they are deploying 34 electric rubber-tired gantry cranes from Kona Cranes.
And for anyone who hasn't been to a deep water port, a rubber-tired gantry crane is this massive piece of machinery that is literally 6 or 7 stories tall.
Jeez.
It drives over stacks of shipping containers, picks them up, and moves them. So the sheer mechanical force required to lift a fully loaded shipping container that translates into a massive electrical draw.
Right, so an operations manager can't just plug 96 heavy-duty tractors and 34 multi-ton cranes into the local utility grid.
Oh no, the utility company would take one look at that demand, laugh at you, and tell the port that it will take 5 years and tens of millions of dollars to trench new transmission lines and build a dedicated substation.
Right, and that utility bottleneck is what solves almost every major commercial electrification project.
It is the main hurdle.
The grid simply wasn't designed to deliver gigawatts of power to a single parking lot. But the workaround the industry has developed is honestly brilliant. We're seeing companies like OptiGrid partnering with Synop to deploy battery-integrated DC fast chargers. Let's break down how that physically works, because this is where that mobile power bank concept gets supersized. Instead of a charger being just a conduit, a wire that passes power from the grid straight to the vehicle, the charger itself contains a massive internal battery.
Exactly. It acts as an energetic shock absorber. So the charger connects to the existing low-voltage grid, and it just pulls a tiny, continuous trickle of power 24 hours a day, storing that energy in its internal battery bank.
Okay.
And because it's only pulling a trickle, it totally bypasses the need for those massive, expensive utility upgrades.
Oh, I get it. So, but when a heavy-duty terminal tractor pulls up, the charger stops pulling from the grid and just dumps the stored power from its internal battery directly into the truck at lightning speed.
Precisely. It bypasses the grid's limitations entirely. And because you don't need a new substation, these chargers can be deployed in weeks instead of months or years.
That is incredible. But the hardware is only half the equation right. You have to orchestrate when these batteries fill up and when they empty out.
Right, which is where the artificial intelligence comes in.
Yeah, the Synop software. There's this fascinating layer of software being layered over this hardware. Synop uses AI for predictive load management.
Right.
The software analyzes the fleet's schedule, the utility rate structures, even local weather patterns, and it automatically tells these battery-integrated chargers to buy power from the grid when rates are rock bottom.
Like when the wind is blowing at 3 a.m.
Exactly. It then uses that cheap stored power to charge the trucks during the afternoon peak when utility rates skyrocket. I read that fleet managers are cutting their energy costs by over 50% doing this.
Over 50%. And they aren't even lifting a finger. The capital markets are definitely recognizing that bypassing this utility bottleneck is the key to freight electrification.
Yeah, I saw ChargePoly just raised a 23 million euro funding round, led by Meridium specifically for this kind of heavy-duty DC charging.
Right, and we are seeing companies like NG Vianio building dedicated electric truck hubs along major European freight corridors like the A2 and A9 highways in Germany.
Okay, but the truck manufacturers are adapting their mechanical engineering to relieve this grid pressure too.
You have to.
Like, Molly is debuting a heavy electric truck range extender at the IAA Transportation Show. Instead of trying to cram an impossibly large battery into a truck, which takes forever to charge and weighs so much, it cuts into cargo capacity.
Right, the weight issue is huge for freight.
Yeah, they use a hybrid approach. The truck has a battery good for about 400 kilometers,
Okay.
but it also has an onboard combustion range extender that acts as an electrical generator, providing another 400 kilometers. So it physically generates electricity on the go to keep the battery topped up.
Meaning the truck doesn't have to rely entirely on finding a multi-megawatt fast charger out on some rural highway.
Exactly.
It is a very practical bridge technology. It acknowledges that the grid just cannot support pure electrification of heavy freight everywhere right now.
Right. But here's where it gets really interesting, because there's a paradox here. If you look at the passenger vehicle infrastructure in Europe right now, the number of physical chargers is actually outpacing the number of EVs on the road.
That's right.
I was reading the Auto Tech Insight report, and it says the physical build-out has been incredibly aggressive. So it makes you wonder, like, are we overbuilding? Is all this panic about grid capacity actually overblown?
Well, this raises an important question about the distinction between the quantity of infrastructure and the capacity of the infrastructure.
Okay.
Because having a million charging cables bolted to the sidewalk doesn't mean the local electrical grid can physically push power to all of them simultaneously.
But I see. It's like having 100 faucets in your house, but only a half-inch water pipe connecting your house to the city water main.
Yes.
You can turn on all 100 faucets, but you're only going to get a trickle out of each one. The physical connection to the source is the bottleneck.
That is the perfect analogy. The grid's water main, so to speak, is maxed out. And we are watching this play out in real time right now in Hungary.
What's happening in Hungary?
So charge point operators there, like MOL, are having to actively throttle their hardware. They have these high-end 150 kilowatt fast chargers, but between the evening peak hours of 5 p.m. and 10 p.m., they are using software to dial the output down to 100 kilowatts.
Wow.
And they are raising the prices during that time.
Just to prevent the local power grid from melting down, because everyone in the city is plugging their cars in right when they get out.
Exactly right, when they are turning on their air conditioning and cooking dinner. The traditional utility response would be to lay more copper wire upgrade transformers and increase the size of the water main.
But that is too slow, too expensive, and incredibly disruptive to build out in urban environments.
Right. So the modern solution is that charging must become a grid-native service. The chargers and the vehicles have to communicate with the grid in real time to balance the load with software.
And this brings us to V2G, or vehicle-to-grid technology, which is finally moving from a conceptual idea into mainstream reality.
It really is.
VWLE is launching a V2G package in Germany right now. And Hyundai Motor Group just launched a service called All Day Energy. It's a global V2X service starting in the UK via the Kia app to handle smart charging vehicle to home and vehicle to grid.
And the mechanics of V2G fundamentally rewrite how we think about a car. I mean, for the last century, a parked car was just a depreciating asset sitting idle in a driveway.
Right, doing nothing.
But an electric vehicle is essentially a massive, highly sophisticated lithium-ion battery. So if a utility grid is nearing collapse at 6 p.m. on a hot day, V2G software can pull a tiny fraction of power from a million parked cars simultaneously.
The grid borrows power from the cars to prevent a blackout, and then repays the vehicles by recharging them at 2 a.m. when demand is low.
Exactly when wind turbines are generating excess power and no one is using it. But to orchestrate that ballet of electrons, utility companies need visibility.
They need to know what's out there.
They need to know exactly how many cars are plugged in, what their state of charge is, and when the owner actually needs them to be full.
And that's the software shift we are seeing with Synob. They partnered with WeaveGrid to integrate with their Disco software.
Yeah, the Disco software.
Which gives utility companies visibility into commercial charging loads, orchestrating grid capacity from the bottom up. It essentially gives utility companies a massive digital dashboard to match the electrical draw to the grid's real-time capacity.
It turns the massive electrical demand of EVs from a grid-breaking liability into a stabilizing asset.
Wow.
There's actually a pilot in the Gelderland province of the Netherlands running across 12,000 Vattenfall and Allego chargers. They are literally paying EV drivers to ease grid congestion.
Paying them.
Yes, they pay them to allow their charging speeds to be modulated. The flexibility of the vehicle's battery now has direct monetary value to the grid operator.
That is wild. So what does this all mean for the immediate future?
We have consumer maps like AAA filtering EV chargers on their trip canvas and tour book guides to help people find the physical plugs, but the technology is moving faster than the maps.
Much faster.
Because the software can be as smart as it wants, but it still relies entirely on highly advanced physical components.
Yes.
I was reading an interview on the Senat blog with Shanna Patadia, she's their head of business development, and she brought up a point about autonomous vehicles that totally reframes the issue.
Oh, the energy draw of AVs?
Yeah, she points out AVs are incredibly inefficient energy hogs because of the onboard computing power required to constantly process high-definition cameras and LiDAR and radar.
Right, the continuous computational load is just massive. I mean, a standard EV might get, 4 miles per kilowatt hour, but an autonomous vehicle might get half that because the computer is consuming so much power just to see the road.
Wow. And she asks, if all these AVs operate in crowded city centers, won't they melt the downtown grids? Oh, absolutely. If you have thousands of autonomous robotaxis operating in a city, you cannot just conjure megawatts of power in downtown London or San Francisco to build a dedicated charging depot.
Right. The real estate is astronomically expensive, and the thermal dynamics of pumping that much juice into a confined space would literally melt standard copper cabling.
Yeah, downtown depots just won't work due to space and power constraints. We will need intense hardware interoperability and shared charging.
Meaning a robotaxi has to be able to plug into whatever charger is closest, regardless of the brand.
Exactly. And this entire ecosystem, the AI load management, the autonomous navigation, the V2G communications, it all relies on one critical piece of hardware, which is the semiconductor.
Ah, yeah.
And this shifts the geopolitical focus entirely. The industry has actually coined a term for this new geopolitical reality. They call it pack silica.
Pack silica.
Yes, historically, automakers spent their time worrying about securing supply chains for raw steel and crude oil. Today, they worry less about steel and oil and more about lithography.
Right, printing the microscopic circuits.
And they worry about raw materials like gallium. The national origin of the microchip buried inside a simple door controller is now a matter of international trade security.
Which exposes them to a totally new kind of fragility.
But interestingly, those supply chains are proving to be surprisingly resilient. A magnitude 7.1 earthquake recently struck Kumamoto, Japan, which is a major hub for semiconductor manufacturing.
And in the past, a disaster like that might have shut down global auto production for months.
Right, but the initial assessments showed limited facility damage and a very quick resumption of semiconductor production.
Huh.
They are learning how to build physical resilience into these delicate supply chains.
And the components they're producing are enabling charging speeds that, frankly, defy logic. Like Hongqi, a Chinese automaker recently tested a new high-performance battery that charges from 10% to 70% in 3 minutes and 41 seconds.
3 minutes and 41 seconds is an astonishing engineering feat. When you force electrons into a battery cell, that quickly, it generates massive amounts of heat.
I'd imagine it would just catch fire.
It would, without highly advanced liquid cooling and specialized chipsets regulating the voltage in milliseconds, it would simply catch fire.
Right. And if 3 minutes is still too long for you, NIO just opened its 4,000th battery swap station in Quanzhou, China. This is their 5th-generation architecture.
All right, where you don't even plug the car in.
Yeah, you just drive over a platform, a robotic mechanism unbolts your depleted battery swaps in a fully charged one, and you drive away.
In the time it takes to wash your windshield.
Exactly. Or we can look at the wild frontier of wireless tech. A company called Hevo just received a U.S. patent for dynamic wireless roadway charging. They are literally designing systems to charge electric vehicles while they're moving.
Right, embedding the coils beneath the asphalt.
Yeah.
So the infrastructure interacts with you dynamically as you move through the environment.
Right. It completely redefines the concept of infrastructure. So let's pull all of these threads together. We started with this idea of a simple mobile power bank arriving to help a stranded driver. But what we've uncovered today is that the transition to electric vehicles, EV infrastructure, is no longer just a plug in a wall.
Not at all.
It is a highly intelligent, mobile, and dynamic ecosystem that is fundamentally changing how the world manages energy. So before we wrap up, do you have a final thought to leave us mulling over?
I do, yeah. We talked about how EV owners in the Netherlands are already being paid to help balance the grid, right?
Right.
And with major players like Hyundai and VW aggressively pushing vehicle-to-grid technology, consider this. In the near future, the primary financial value of your car might not be transportation at all.
Wait, really?
Yeah, your car could become an autonomous energy trader. Picture your vehicle buying cheap power at 2 a.m. from the local utility and storing it, and then selling it back to the city grid at a premium at 6 p.m. while you eat dinner.
Wow, running an arbitrage business in the driveway.
Exactly. Your vehicle might just pay its own lease.
That is an amazing concept. I love that. Well, thank you all for joining us on this deep dive. Next time you see an EV quietly parked on the street, remember the invisible revolution happening right beneath its tires. See you next time.